With the ongoing movement towards autonomy and sustainability, our group decided to join in on the trend for our electronics or mechanical engineers term project. We made the glider self-leveling and self-correcting using an IMU and PID control system, where the glider would fly straight and level, adjusting to its surroundings. The following is a list of materials we used to complete our project. For more details about our component selection, see the description. Here's an overview of the circuit used to control our glider. The heart of the circuit consists of an Arduino Nano. The Arduino is responsible for receiving the accelerometer and gyroscope data, and using feedback control, turning the data into servo commands to the glider's ailerons, elevator, and rudder. A Raspberry Pi 3 is used to record all of the Arduino data for the post-flight analysis. On the power distribution side, each microservo has a peak current draw of 250 milliamps, so the current from the 5-volt input voltage supply on the Arduino is not enough to power all servos at once. To solve this issue, we resorted to a separate battery pack as our power source using a 1500 mAh LiPo battery. As the supply voltage from the battery was too high for the servos, a step-down converter was used to supply 6 volts of DC power to the circuit. First, we did some research and testing on the circuit topology. We organized the fuselage of the glider to fit everything inside. Then we wrote up the most important part, our code. The IMU is connected to the Arduino and reads input accelerometer and gyroscope data, displaying it on the serial monitor. Using a PID control loop, the measured data is compared to the preset desired references that we want to maintain. Adjustments are made using the servos to control the ailerons and elevator on the glider, reducing the difference between the real-time and the reference values. Since the reference values are set level to the ground, the glider will correct itself for any deviations and attempt to remain level to the ground in flight. Once we were sure of everything, we did all our soldering and testing and assembled the glider. Our first couple attempts were pretty bad because we didn't have our PID properly tuned. Over time, we adopted an experimental tuning method called the Ziegler-Nichols method to yield an optimal response. In this attempt, you can see the oscillation in the glider's wings, which is a sign that the KP element in the PID control was set a little too high. We tinkered around a bit more with the 3 PID elements and we made some progress. And finally, we obtained some constants that gave us consistently smooth flights.